Good morning, everyone. Thank you for joining me today. I'm David Lee, and I'll be sharing interactive ABCs with American Sign Language using Yolov5 for my General Assembly Capstone project. Here's our agenda. I'll be covering an overview, the problem statement, initial challenges, the data collection process, pre-processing, modeling and inference, conclusions, next steps, and we'll finish off with a Q&A. I'd like all of us to think about a few questions for a moment. Have you ever considered how easy it is to perform simple communication tasks like ordering food at a drive-thru, discussing financial information with a banker, telling a physician your symptoms at a hospital, or even negotiating your wages from your employer? What if there was a rule where you couldn't speak and were only able to use your hands to get your point across every single day? The deaf community cannot do what most of the population take for granted and are often placed in degrading situations due to these challenges they face. Access to qualified interpretation services isn't feasible in most cases, leaving many in the deaf community with underemployment, social isolation, and public health challenges. To give these members of our community a greater voice, I have attempted to answer this question. Can computer vision bridge the gap for the deaf and hard of hearing by learning American Sign Language? If we can prove that ASL can accurately be interpreted through a machine learning application, even if it's just the alphabet, we can mark a step in providing greater accessibility and educational resources for our deaf and hard of hearing communities. To tackle this problem, a few challenges would have to be addressed. The first is the amount of data that's required to prevent an overfitting model. Although there's no definitive number that constitutes as enough, having over 1,000 images per category is generally accepted for image classification problems. Inference speeds on predictions and the model size also need to be considered, as having a model that doesn't operate smoothly may result in a poor user experience. And mobile devices currently have limitations on the models that can operate on them. The object complexity of the hand is also an unknown. Several existing models are, for the most part, inanimate or easily distinguishable objects like a sports ball, tennis racket, or even red and white blood cells. Although human object detectors already exist, the several shapes the hand makes may add complexity in understanding the letters of the alphabet on the same hand. First, we'll address the data. The decision was made to create an original data set for a few reasons. The first was to mirror the intended environment of a mobile device or webcam. These often have resolutions of 720 or 1080p. Several existing datasets have a low resolution and many do not include the letters J and Z as they require movements. A letter request form was created with an introduction to my project, along with instruction on how to submit voluntary sign language images with Dropbox file request forms. This was distributed to social platforms to bring awareness and to collect data. In total, 720 images were collected, with the letter J having the most, with a count of 38. Something to note is that several of these were of my own hands due to time constraints. To help generalize this small image dataset, image augmentation techniques were performed on all of these images. There are 3 main augmentation techniques available: basic manipulations, deep learning approaches such as GANs, and meta-learning, which is a combination of the two. Basic image manipulations were chosen as deep learning and meta-learning techniques require far greater computational resources and time, and any increase in accuracy often doesn't justify the cost of this approach. The strategy was to manually input bounding box coordinates around each of the images, then making the images square to keep a consistent canvas size that we can work with. A probability of transformations function was then created to oversample and data warp our images into new ones that we can use while creating new bounding box coordinates for all of the images. Here's the result of one of the pictures. As you can see, specified degrees of rotation, shifts in the image locations, blurs, horizontal flips, random erase, and a variety of color transformations are applied. These will help our model depict important features to choose for each letter. Using these techniques, our original data increased to 18,000 images. According to Acquiring a large quantity of original images would help in creating a better model, but these transformations should help in mitigating an overfit model. To address acceptable inference speeds and size, Yolov5 was chosen for modeling. This was released in June 10th of this year and is in active development. Yolov5 is said to be faster and more lightweight, with accuracy on par with Yolov4, which is widely considered as the fastest and most accurate real-time object detection model. YOLO was designed as a convolutional neural network for real-time object detection. It's more complex than basic classification, as object detection needs to identify the objects and locate where it is on the image. This single-stage object detector has three main components. The backbone basically extracts important features of the image. The neck mainly uses feature pyramids, which help in generalizing the object scaling for better performance on unseen data. The model head does the actual detection part, where anchor boxes are applied on features that generate output vectors. And these vectors include the class probabilities, objectness scores, and bounding box. Here's what it looks like. During the testing phase, the conditional class probabilities are multiplied by the individual box confidence predictions. This gives us the class-specific confidence scores for each box. And these scores encode both the probability of that class appearing in the box and how well the predicted box fits the model. The Yolov5 family has 5 different models to choose from, and selecting the right balance between speed, accuracy, and size is important for the practical use of this application. After a few test runs, I chose to use the N model for my test, as inference speeds it'll be more important that the inference speeds are fast than having a larger model with a higher accuracy but slow user experience. Transfer learning was applied while training my model with the Yolov5 M pre-trained weights. Even though pre-trained weights were incorporated, the model was trained with 300 epochs with an image size of 1024 pixels. The mosaic images show an instance of the training batch. The final validation set successfully created new bounding boxes with labels and prediction confidence values. To understand mean average precision scores, you first need to understand intersection over union. Basically, it's the area of overlap between the actual bounding box and the predicted bounding box divided by the union of the two. It gives us a confidence level in the prediction and counts the ones over a 50% confidence threshold. The number highlighted in yellow is the mean of these levels between 50% confidence and 95% confidence in steps of 5%, which shows how well the object detection model is performing on our data set. Here are the metric charts during our model training. As there isn't a rise in loss values, it shows that the model is not overfit, and we probably could have trained for more epochs. Overall, these charts look promising, but inference tests will determine if the model's precision is good enough for a deployable model. I had reserved a test set of my son's attempts at each letter, and that was not included in any of the training or validation sets. In fact, no pictures of hands from children were used for training the model. Ideally, several more images would help in showcasing how well our model performs, but this is a start. As you can see, several of these images have correct labels and the bounding boxes look great overall. The letters G, H, J, and Z did not receive a prediction, and the letter D was predicted as F, E was predicted as T, P was predicted as Q, and R was predicted as U. Even though the original image set was only 720 pictures, the implications of these results bring us to a very exciting conclusion. Computer vision can and should be used in marking a step in greater accessibility and educational resources for our deaf and hard of hearing communities. Here is a video of my attempts at each letter using our model. Even though several images were on my hand for training, the fact that the model was able to perform pretty well on such a small data set and still provide good predictions without feeling slow is very promising. More data will only help in creating a model that could be utilized in a wide variety of new environments. As shown in this clip, even a few letters that were partially off-screen had good predictions. Probably the most surprising thing is that the letters J and Z, which require movements, they were recognized by my model. Additional tests were done and that basically showed that the model works even for left-handed users. And that particularly was great news because nearly all of the original 720 images were right-handed. The augmentations pipeline, which had a 50% chance of flipping the images horizontally, worked. In the center, we have my son's hand, who wasn't used for the training set, and the model still performs well here. Simultaneous letters were also detected. Although sign language is not used like the video on the right, it shows that multiple people can be on screen, and the model will be able to distinguish more than one instance of the language. That being said, there were limitations I discovered in my model. The biggest one is distance. As many of the original pictures were taken from my phone of my hands, the distance of the hand to camera was very close, negatively impacting the inference at further distances. There also seems to be a negative impact on detection with new environments. The video in the center are from volunteers that, again, were not used in any of the model training. Although the model picks up a lot of the letters, the prediction confidence levels are lower, and there are more misclassifications present. I did a test on the right that verifies that different backgrounds hurt the model's performance. These conclusions bring us to our next steps. I believe this project is aligned with the vision of the National Association of the Deaf in bringing better accessibility and education for this underrepresented community. If I'm able to bring awareness to the project and partner with an organization like the NAD, I'll be able to gather better data on people that can speak this language natively to push the project further. The technology is still very new, and the model I have trained for this presentation was primarily used to find out if this would work. I'm really happy with my initial results, and I've already trained a smaller model that I'll be testing for mobile deployment in the future. I'll end with this. I believe computer vision can help give our deaf and hard of hearing neighbors a voice with your support. Consider this. Not every advancement in technology is used for good, but this one is. Thank you. I'll open the floor to questions.
I have a question. I noticed that when you switch from letter to letter, sometimes it has you pulling up a J as you switch, right?
Yes.
Notice that? What is that something you think you can fix going forward to, for complete sentences, something like that? Because the transition's obviously important.
So the model is making very fast inference speeds, and depending on the training set that was used for the model, it's basically whichever one gets the higher probability of what letter it is at that very moment of prediction. So I could increase the confidence threshold. Say, for example, I want to show the letters that are above a 40% confidence threshold, then they'll show the image. If I increased it, then the model will have to be more certain that it's a certain letter, and that may fix some of the problems.
So piggybacking on his question in the same vein, so that score, it was updating in real time, basically.
Yes, it was.
Is there, I don't know, counter what he was bringing up, is there a way to maybe extend the time period that it's scoring on, if that makes sense?
So the time, all of that is real time. Really, we would have to play around with, first of all, making a model with more images, more data would definitely help the model. But also, with the additional data, I would certainly increase the confidence threshold, and that really should solve the glitches with the letters predicting different letters.
Gotcha. And I'm not familiar with ASL very much. There's the alphabet, and then there's also sign language for words, correct?
Yes. So this is just the first step. Like, I wanted to make sure, hey, all the different symbols that a hand makes, will it be able to predict well? I had no idea going into this project and it was very exciting to kind of discover as I went through and see that it actually does work.
Yeah, cool. Okay, thank you.
Thank you.
So David, how quickly could you then be able to adapt your model to like the 25 different kinds of sign language? Because isn't there like 25 different versions?
There are different versions of sign languages all around the world. Obviously, if this were a project that takes off, I would want to start with this language first and make sure that I can get very good feedback from the overall community. And then at a certain stage, I would push forward to different, to expanding that.
And where can we apply to work on this, Victor?
The first thing is to get the word out. Honestly, any traction on this project, partnering with the NAD. I mean, I've already looked at some of the contents, but when I eventually bring this to the social presence, I mean, the better the word gets out there, the greatest chance that this actually can happen.
Sign me up.
Thank you.
Just need to get a grant. There's lots of grants out there for this stuff.
Yeah, that'd be great.
You gotta find a grant writer. I hate it. I'm not doing that. Don't sign me up.
Really, really awesome project, David. Thank you so much.